Welcome to the new light board and welcome to multivariable 13.3 on arc length and curvature. So we've been talking a lot about these space curves, these parameterized space curves in 13.1 and 13.2, and it's time to start doing some new things with them. Now, back in BC calculus, you might have remembered we did arc length, or you did arc length, and you might remember that if you had some function, right, where you've got an x of t and a y of t, right? This old ye old parametrics, that we define the arc length this way. It was from a to b, square root of dx dt squared plus dy dt squared dt. And you might guess then, therefore, that in 3D, it would look very similar. And in fact, rather than rewriting the whole thing again, in 3D, we can just extend it. Plus dz dt, the quantity squared dt. And the rationale here is, if you kind of see in red this space curve, what we're really doing is we're kind of considering, we're sort of taking the limit of chopping it up into little line segments. And you might imagine, right, what's the distance between, what's the length of this line segment? Well, the length of this little line segment might be, delta x squared plus delta y squared plus delta z squared. And so we're going to do that. Now, there's a couple things I want to note about this integral before we do one. First of all, the bounds of the integral a and b, these are in t. These are in our parameter space from t equals a to t equals b. The other thing you might notice is that, well, we've got an x derivative, a y derivative, and a z derivative all squared. This actually kind of looks like the magnitude of a vector, right? It's the square root of a bunch of things squared. And so what we'll often do is we'll actually remember that the arc length is the integral from t equals a to t equals b of the magnitude of r prime dt. Because of course the magnitude of r prime, well, there dx dt is the x component, dy dt is the y component, and so on. I also really like this interpretation of arc length, because one way that this kind of makes me think is, if we take our space curve, right? Here's a random curve through space. Arc length you can kind of think of as like a ruler, measuring little tick marks, like a flexible measuring tape, along the curve. It's measuring your distance along the curve. And so what I like about this is that, again, if we interpret r prime as our velocity, the magnitude of r prime in a physics perspective is our speed. This is just speed times change in time. And what that's telling you, right, is that if you drive for 60 miles per hour for 2 hours, you will drive 120 miles. Now, your displacement in a physics sense might not be 120 miles, right? You might spend that time driving in a circle, but the distance you travel along that arc will be 120 miles. So it's kind of the speed as measured along the road. Sometimes you will also, by the way, in your textbook and other places, see L, instead arc length called S, the letter S. So you'll sometimes also see that the magnitude of r prime is called ds dt. It's the time derivative of arc length. All right, so let's do a little example of one of these. So let's take our good old-fashioned helix, and I'll draw our helix here. And what we want to do is we're just going to take kind of the first loop, if you like, of our classic helix. So we're going to start here at 1, 0, 0, and we're going to loop around once up to this point, which is of course 1, 0, 2 pi, reminding ourselves that we've got r of t. This is our classic helix, cosine t I hat plus sine t j hat plus t k hat. And we want to ask ourselves, what is the arc length of just this little first loop? Okay, we're going to go around 2 pi. So let's go, first of all, go ahead and find r prime, because we do have to find that. So that's going to be negative sine ti plus cosine tj plus just 1k. And if I go ahead and find the magnitude of r prime, it's going to be the square root of, well, the negative isn't going to matter because we're squaring it. So it's going to be sine squared t plus cosine squared t plus, well, 1 squared. And as reminding ourselves that sine squared plus cosine squared always gives us 1. This is 1 plus 1, or root 2. Notice that it's constant. What that means is that kind of, if you imagine our point being an object traveling around this curve, according to this equation, it does so at constant speed. Well, not constant velocity, constant magnitude of velocity, constant speed. All right, so that makes actually our final integral relatively straightforward. We're going to go ahead and plug it in here that the arc length then is going to be the integral from 0 to 2 pi. How do I know it's from 0 to 2 pi? Well, remember, if I look at my z coordinate here, it's just tk. So my t goes from 0 up to 2 pi. Of the magnitude of r prime, dt, well, it's just a constant dt. So I'm going to get 2 root 2 pi as my answer. So if you actually took out your flexible measuring tape, which you all have, obviously, for measuring clothing and things like that, if you took out a flexible measuring tape and laid it along this curve and measured very precisely that distance, you would get exactly 2 root 2 pi. Now we turn our attention to curvature, which is an attempt to describe kind of exactly what it sounds like, which is how curvy is a particular space curve. You can kind of see I've drawn 2 ones up here, one that is not very curvy, well, it's not totally straight, not very curvy, and one that is extremely curvy. However, being budding mathematicians, we'd like to do a little bit better than not very curvy and extremely curvy. So what I want us to do is I want us to imagine that we're driving down these roads, right? Kind of similar to how the magnitude of r prime is like the speed of your car, and arc length is the distance measured along the road. Let's imagine we're driving down these roads, right? What would be the difference in your experience driving down these 2 roads? Well, hopefully it's clear your job steering is going to be much more difficult for the second curve. So let's see if we can kind of quantify that a little bit. And instead of thinking about a literal steering wheel, we're going to ask, well, what determines your steering? And I've actually drawn in a bunch of these things. The direction that you're going is changing all the time. And so in lieu of our steering wheel, we're going to use a mathematical steering wheel, namely the unit tangent vector. So if the unit tangent vector is changing very rapidly, we're going to say we have high curvature. And if it's changing very slowly, we're going to say we have low curvature. And we actually do have a way to calculate this. And it's with this equation, which I don't want you to write down. Well, you can write it down if you like. It's part of your notes. But we're not going to use this one very much in class. It's curvature, which is like a little kappa, a little funny k, is the magnitude of the rate of change of the unit tangent vector with respect to arc length. That is, the reason it's ds, dtds, is it's asking every time you take the same step along your curve. So every time, for instance, I move 1 meter along my curve, how much do I have to adjust my steering wheel for every meter that I go? However, this is of very little use calculationally, because calculating for an arbitrary space curve, calculating the unit tangent vector can be a little bit difficult, and then finding the derivative of the unit tangent vector with respect to arc length is no bueno. So we're going to see if we can do better than that calculationally. Intuitively, super great. So we're going to get 3 equations. Each one is going to be more calculationally useful and less intuitive. So intuitively, that one's great. How quickly is your unit tangent vector changing? However, let's get some calculations done because you have to do your problem set. We're going to employ the chain rule. And we're going to start with something seemingly unrelated, with the derivative of the unit tangent vector with respect to our parameter t. And remembering that our arc length is changing with t, the distance we've moved is changing with t, we're going to make a quick little chain rule, change of variables. And so we're going to note, hey, look, dTds appears right there. So I'm going to instead write my curvature this way. I'm going to write it as the magnitude of dt, the unit tangent vector dt, over ds dt. And then I just want to note, we know what ds dt is. Ds dt is r prime, is the magnitude of r prime. So actually, I should be clear about this, that this is magnitudes. Wow. Great. All right, so it's the magnitude of t prime over the magnitude of r prime. So this is a little bit better. We can still find t, take its derivative. We can find r prime pretty easily. This is better, but it's still not great. Because calculating, we'll do it in class, but generally speaking, calculating the derivative of t hat is, again, no bueno. So I'm going to give you a third equation without proof. The proof is in the book. And this is the one we're mostly going to be using. We're going to be mostly using this one, which is that curvature is equal to the magnitude of the cross product, r prime cross r double prime, all over the magnitude of r prime cubed. Again, the proof is in the book, but this is the one we're most often calculationally going to be using because it is by far the most convenient and the most consistent. So let's do a quick little example here. And we're actually going to do, as our example, an object just moving in a flat circle. So we're going to take the unit, not the unit circle actually, we're just going to take a circle of radius a in the xy plane. So I'm going to adopt an r of t here, which is going to be a cosine ti hat plus a sine t j hat, and there's going to be no k hat. That's going to be plus 0 k hat because I just want it to be in the xy plane. And this is going to be a circle of radius a. And then our goal is to find the curvature here. So let's go ahead and take some derivatives. We'll go ahead and find r prime. Not too hard. Negative a sine t. This is plus a cosine t. We'll go ahead and find r double prime, which is negative a cosine t minus a sine t. We will also go ahead and find the magnitude of r prime, which will be root a squared sine squared plus a squared cosine squared. Well, a little bit of factoring should convince you that this is just a squared, but it's the square root of a squared. So the magnitude of r prime is just a. The last thing we need is this cross product, r prime cross r double prime. And again, this calculation is a little tedious. You got to do a cross product, take a bunch of derivatives, but it always works and it's fairly straightforward. So we're going to put in r prime negative a sine t, a cosine t 0, negative a cosine t, negative a sine t also 0. Hopefully I can convince you and work it out for yourself if you don't believe me that there's only a k hat component to this cross product, which kind of makes sense because everything else lies in the xy plane. And this will give us a k hat component of a squared sine squared t plus a squared cosine squared t, or it's just a squared k hat. So putting it all together, what is the curvature here? Well, it's going to be the magnitude of that cross product. So we get just a squared all over magnitude of r prime cubed, a squared over a cubed, or 1 over a. That the curvature is inversely proportional to the radius. And you can kind of think about that as the radius of your turn gets bigger and bigger and bigger. If you make a bigger and bigger circle, you don't have to turn your steering wheel as much, right? It's not as curvy. This concept actually applies to lots of other curves. If you kind of reverse the relationship a little bit, and we look at the radius of some circle equal to where the radius is 1 over the k, we have a special name for this. This is called the radius of curvature. And it is equal to the inverse, to the reciprocal of the curvature. And the logic here of what this means is, imagine I have some arbitrary space curve here. At some places, the curve is relatively flat. I can fit a big circle tangent to the curve. In other places, the curve is very tight, and I can only fit a tiny circle in. Here I can fit a medium circle in. The radius of curvature is kind of the radius of a turn. The radius of the turn that the curve is making at this point. So if you were, for instance, designing a racetrack, the curvature of your track, if you calculated it, would literally be inversely proportional to the turn radius required to make that turn. So the radius of curvature turns out to be a useful feature for describing curves in general. So again, we've got 3 equations for curvature, but really in class, practically speaking, this is the only one we're going to use. Even though intuitively, this is the one we're always thinking about. We're always thinking about how rapidly are we steering as we make it through as we kind of walk along our curve.